You stand in front of a pyramid, 46 centuries old, 2 million stone blocks, each one weighing 2 tons, cut with copper tools and bronze chisels, placed so precisely that a sheet of paper won't fit between them. No mortar, no machinery, no blueprints on papyrus that survived, just mathematics, hidden in every angle, every measurement, every ratio that makes your brain say this is beautiful without knowing why. The ancient world built monuments that modern engineers study with laser scanners and finite element analysis, trying to figure out one question: how did they know? Not just how they moved the stones, how they knew the math, how civilizations without calculus, without algebra as we know it, without even the number 0 in some cases, encoded geometric principles so sophisticated that we're still finding them. Pyramids that aligned to true north within 3/60ths of a single degree, Greek temples with curves so subtle they correct for optical illusions in your brain, Roman domes that remain the largest unreinforced concrete structures on Earth after 1900 years, Inca walls that survive earthquakes that flatten modern buildings. The math was always there, we just couldn't see it. If you value documented ancient engineering and hidden mathematics like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from the Rhind mathematical papyrus, housed in the British Museum and dated to 1650 BCE. The Moscow mathematical papyrus from 1850 BCE, held in the Moscow Museum of Fine Arts, peer-reviewed. Engineering analysis published in the Archive for History of Exact Sciences, Volume 65 from January 2011, and structural analysis from the Journal of the Society of Architectural Historians. These aren't general history books. These are primary mathematical documents from ancient Egypt and modern engineering studies that reverse engineer what the builders knew. Now back to the information. The pyramids rise from desert bedrock on the Giza Plateau. The Great Pyramid of Khufu. Base, 230 meters. Each side measured in royal cubits. The royal cubit, 52.3 centimeters. Not arbitrary. Derived from the human forearm, elbow to fingertip, but standardized. Carved into granite measuring rods. Checked against master cubits kept in temples. The pyramid builders divided the cubit into 7 palms, each palm into 4 fingers. 28 fingers per cubit. This gives you the unit system. The construction requires something else, the seked, recorded in the Rhind mathematical papyrus, problem 56. The seked measures slope, not as we do today with rise over run. The Egyptians measured run over rise. How many palms horizontal for every cubit vertical? The inverse of our slope. The Great Pyramid has a sect of 5 1/4 palms. This creates a face angle of 51 degrees, 52 minutes. Not 51 degrees, not 52 degrees. 51.867 degrees, precise to fractions. Half the base is 220 cubits, or 1,540 palms. Divide by the sect 5.25. You get 280 cubits height. The actual Great Pyramid, base 230.34 meters, height 146.6 meters. The ratio of perimeter to height times 2 gives you 6.28. That's 2 pi, accurate to within 0.04 of 1%. Egyptians didn't have the symbol pi, didn't need it. They encoded it in the measurement system. 28 fingers in a cubit. The seked denominator divides evenly into 28. 20 divided by 28, 21 divided by 28, 22 divided by 28. These are the inverse slopes of 4th dynasty pyramids. The bent pyramid of Snefru uses both 21 over 28 on the lower section and 20 over 28 on the upper section. They changed the angle mid-construction, not because they miscalculated, because the slope was too steep for the foundation. The mathematics told them before the structure failed. The formula: 1/3 times height times the sum of the squares of both bases plus the product of both bases. The scribe assumes a height of 6 cubits, a bottom square of side 4, a top square of side 2. He computes 2 times 2 plus 2 times 4 plus 4 times 4. Gets 28, multiplies by 1/3 of the height, which is 2, finds 56 cubic cubits. The formula is correct. This is 1850 BCE. The papyrus shows no derivation. The scribe knows it, uses it, treats it as standard knowledge. European mathematicians independently derived this formula thousands of years later. The Egyptians had it and used it for designing pyramids that tapered as they rose. Granite from Aswan, 800 kilometers south for the king's chamber, transported on wooden sledges with water poured underneath to reduce friction. Experimental archaeology by Dennis Stocks in 1998 and Jean-Pierre Protzen in 1985 shows copper saws with quartz sand abrasive can cut granite. Slowly. A linear meter of cut takes days of continuous work, but it cuts. The tool marks are in the stone. Tubular drills with copper and sand cut cylindrical cores. The British Museum has core samples from pyramid construction. They show spiral groove marks from the drilling process. Rotation speed, pressure, and abrasive combine to cut the hardest stone with Bronze Age technology. not alien technology, mathematics, and persistence. How? No magnetic compass. The magnetic North Pole moves. True north is the Earth's rotational axis. Egyptian astronomers used circumpolar stars, stars that never set below the horizon. They built a circular wall, leveled the top surface with water channels, and watched a star pass behind the wall on the eastern side and appear on the western side. The midpoint between rise and set points gives true north. Alexander Thom, the Scottish engineer who analyzed Stonehenge, estimated the Egyptians could achieve arc-minute precision with this method. The pyramids prove he was right. Cut channels in bedrock, filled them with water, marked the water level, and cut the rock down to the marks. Water finds its own level. Physics does the work. The mathematics tells you where to measure. A level foundation means the geometry stays true. When you stack 2 million blocks, a 1-degree error at the base becomes meters of error at the apex. They couldn't allow error. The mathematics wouldn't let them. Not every block. The core blocks, rough cut from the quarry, used mortar. Gypsum mortar. But the casing stones, the outer surface, fit without mortar. The seams are visible. Put a knife blade in the joint. It won't go. Some joints show gaps measured in micrometers. How? Precision grinding. One block placed against another, rocked back and forth with an abrasive between them over and over until the surfaces mate. Then rotate the block, repeat the process until all edges seat perfectly. Time-consuming, but possible. The evidence is the Great Pyramid still standing with casing stones that survived 4,600 years until humans stripped them for other buildings in medieval Cairo. But the mathematics work. 2 million blocks, 20 years, 365 days per year, 7,300 days. That's 274 blocks per day, 10 hours of daylight, 27 blocks per hour. 1 block every 2 minutes. Not possible with a small crew. This requires thousands of workers working simultaneously on different parts of the structure. The logistics alone demand sophisticated planning. The math behind the logistics: food supply, tool manufacture, stone transport, workforce rotation. The pyramids weren't just engineering. They were industrial project management at a scale the ancient world had never attempted. We don't see the mathematics. The ditch surrounding the stones is 214 meters in circumference, 1,130 feet. The diameter from outer edge to outer edge is 360 feet. Divide circumference by diameter, 1,130 divided by 360, 3.1389. That's pi within 2%. This is 3,000 years before Greeks documented pi in Euclid's Elements in 300 BCE. And 30 gaps, 60 points on the circle, like Babylonian base, 60 mathematics. But Britain in 3000 BCE had no contact with Babylon. Independent development of sexagesimal thinking. 56 holes. 56 is 8 times 7. 7 palms in an Egyptian cubit. Multiple of 7 appears across megalithic Britain. The stones encode astronomical cycles. 56 years is 3 ecliptic cycles. 56 years is close to 3 metonic cycles of the moon. The holes weren't random. They recorded celestial mechanics with pegs moved from hole to hole tracking lunar nodes. Optical correction. A column that's truly vertical looks like it leans outward when viewed from ground level. The taper makes it look vertical to the eye. Same trick the Greeks later used on the Parthenon. But this is 1,500 years before the Parthenon. The Neolithic builders understood how the human brain processes perspective. Aligns with the sunrise on summer solstice. Stand in the center. Watch the sunrise. It rises directly behind the heel stone, June 20th or 21st, depending on the year. This alignment stays accurate within a few days across millennia because Earth's axial precession works on a 26,000-year cycle. The builders chose the location and orientation to encode this moment. They tracked the sun across seasons. They knew the exact number of days between solstices, 365.242 days per solar year. They couldn't write it as a decimal, but they could mark it in holes in the ground and count it with pegs and ropes and observations night after night, year after year. The landscape connecting Stonehenge with Lundy Island in Wales and the Preseli Bluestone quarries. The bluestones, the smaller inner stones, came from Preseli Hills in Wales, 225 kilometers away. Each stone weighs 2 to 5 tons. Why transport them this distance? The stones have unique acoustic properties. Strike them with a hammer and they ring like bells. But the geometry matters too. The distance from Stonehenge to the quarry, to Lundy Island, to Stonehenge forms triangle ratios of 5, 12, 13. That's a Pythagorean triple. 5 squared plus 12 squared equals 13 squared. This is 2,000 years before Pythagoras was born. The base concepts: Pythagorean triangles used in construction procedures from Neolithic circular ditches in Central Europe from the 5th millennium BCE. The knowledge extended to elliptical concepts, approximations for pi and the square root of 2 encoded in the henge dimensions. The square root of 2 appears when you construct a square and measure its diagonal. 1 unit by 1 unit square has a diagonal of square root of 2. 1.414. The Neolithic surveyors used ropes and stakes to construct these ratios on the ground. No written mathematics, but they knew. The stones prove it. When you look at a long horizontal line from a distance, your brain makes it sag in the middle. Optical illusion. The neurons in your visual cortex process the edges differently than the center. To make it look straight, they made it curved. The columns, all 46 of them, lean inward. If you extended them upward, they would meet several kilometers above the Parthenon. Why? Vertical columns viewed from ground level appear to lean outward due to perspective. The inward tilt corrects this. The columns also have entasis. A slight bulge in the middle, about 2 centimeters over 10 meters of height, makes them look straight. A truly straight column looks concave from below. Not the golden ratio of 1.618 as popular myth claims. The facade doesn't fit golden ratio spirals, no matter how many badly aligned diagrams float around the internet. Gary Meisner, who analyzed this with high-resolution photographs in 2020 and published the analysis on goldennumber.net, measured the actual proportions. The decorative panels above the columns show golden rectangles, width to height of 1.618 to 1. Very precise. This part may have used the golden ratio, but the overall building uses 4 to 9 and root 5 to 1 ratios instead. Root 5 is 2.236. It's the diagonal of a 1 by 2 rectangle, easy to construct with rope and stakes. The Greeks loved root 5, appears throughout their architecture. Corner columns are slightly closer to their neighbors than the center columns are. This creates the illusion of uniform spacing when viewed at an angle. The corner columns are also slightly thicker, 2% thicker than the others. Why? The corner columns are viewed against bright sky. The contrast makes them look thinner than they are, when the extra thickness compensates. Every measurement in the Parthenon involves corrections for how human vision works. This required understanding geometry, understanding human perception, and calculating exact dimensions that achieve the desired visual effect. The builders had no textbooks on optical psychology. They learned by experimentation and encoded the results in proportional systems. 4447 to 4438 BCE. Patelikon marble, quarried 16 kilometers away. Blocks transported on wagons pulled by oxen over prepared roads. Each column drum weighs roughly 10 tons. 60 drums required for 8 front columns. 480 tons just for the facade. The blocks fit with iron clamps poured with molten lead. Metal expands when heated, contracts when cooled. Lead contracts and locks the clamp in place. The joints between blocks show incredible precision. Not as tight as Egyptian pyramid blocks, but still measured in millimeters. The Greeks understood that precision in stone cutting meant precision in the final structure. Error compounds. The mathematics demanded accuracy. The entablature above the columns curves to match. The whole building forms a gentle arc when you sight along its length. Modern laser surveys conducted during restoration in the 1980s revealed these curvatures. Every stone block had to be cut to slightly different dimensions to accommodate the curves while maintaining level surfaces where needed. The stonemasons worked from models and measurements, adjusting each piece to fit its specific position. The quality control required systematic oversight. The mathematical planning required understanding the entire structure before cutting the first block. The dome dominates, 43.3 meters in diameter, 43.3 meters from floor to apex, same measurement. The interior encloses a perfect sphere. Sit on the floor, look up. The top of the sphere touches the dome, the sides touch the walls. The geometry is exact. Why? Harmonic proportions. The Romans believed mathematical ratios created beauty and stability. Perfect sphere inside a perfect cylinder. 150 Roman feet diameter, 30 Roman feet oculus, 40 Roman feet door height, all multiples of 10. Clean numbers, easy to work with. But the engineering is the marvel. Volcanic ash that reacts with lime to create hydraulic cement. Hydraulic means it sets underwater or in damp conditions. This property allows massive pores. The Pantheon dome was poured in concentric rings, layer by layer, over several years. The concrete needed time to cure and gain strength. Rush the construction and the dome collapses under its own weight. The Romans understood this. They built the walls first, waited, then built the dome. The aggregate changes with height. At the base of the dome, dense basalt and travertine stone weighs roughly 2,200 kilograms per cubic meter. At the middle, lighter tufa stone and broken brick, roughly 1,800 kilograms per cubic meter. At the top, near the oculus, pumice and crushed potsherds, roughly 1,400 kilograms per cubic meter. Each layer is lighter than the one below. This reduces weight and reduces stress. Mark and Hutchison conducted finite element analysis, published in 1986, in the Journal of the Society of Architectural Historians. They found that if the entire dome used dense aggregate throughout, the tensile stress would be 80% higher. The dome would crack, probably collapse. The Romans knew this without computer simulations. They tested concrete samples. They understood that lighter material at the top meant less load on the base. The Romans approximated this curve with stepped rings visible on the exterior, 7 concentric rings stepping up the outside of the dome. Inside, the surface is smooth. 5 rings of 28 coffers. 28 again. Same number as fingers in a royal cubit. Multiples of 7 appear across ancient architecture. The coffers reduce weight. Each coffer removes several hundred kilograms of concrete. 140 coffers total. Multiply by average coffer volume times concrete density. Removes roughly 50 tons from the dome. 50 tons that would add stress to the structure. Creates a sundial effect. But structurally, the oculus is genius. The opening means the dome doesn't need to support its own weight at the very center where compression forces converge. The ring of concrete around the oculus is 4,535 tons. That weight presses down and outward, and the dome resists by acting like an arch in all directions simultaneously. Every point on the dome pushes against every other point. The structure is self-supporting once the concrete cures. Finished. Medieval legend. Maybe true, maybe myth. The important part. The concrete had to cure before removing support. The Romans understood material science even without chemistry textbooks. They tested and observed. They learned what worked. They encoded that knowledge in construction techniques passed from master to apprentice. The Romans dug down 8 meters, lined the trench with timber forms, and poured concrete mixed with pozzolana cement. This foundation is 15 meters deep for the rotunda. Rectangular trenches for the portico. The pozzolana cement is powerful. Creates a monolithic foundation block that distributes weight across a large area. This prevents settling. The Pantheon has stood for 1,899 years. It hasn't sunk. The foundation math worked. The concrete's tensile strength from samples of similar Roman concrete from Libya, 213 psi. The dome operates well within safe limits. The cracks are stable. They've been monitored for decades. No propagation. The mathematics predicted this. The structure is overbuilt relative to the forces acting on it. This is intentional. Roman engineers couldn't calculate exact stresses. They built with safety margins, large margins. The Pantheon survives because they understood that uncertainty means adding extra strength. Brunelleschi spent time in Rome measuring the Pantheon with calipers and notebooks. He copied the herringbone brick pattern used in the Pantheon's inner shell. He studied how the Romans reduced weight with lighter materials higher up. He applied these lessons to the Duomo. His dome has a 46-meter diameter, larger than the Pantheon, but reinforced. The Pantheon remains the largest unreinforced concrete dome ever built. 1,900 years later, we still haven't exceeded it without steel reinforcement. This is intentional design philosophy. The Inca don't build to dominate nature, they build to harmonize with it. The mathematics support this approach. Each angle seats against an adjacent block. The joint is tight, paper won't fit. How did they achieve this? Multiple theories. One involves reduced scale clay models. Build a model at 1/5 scale, test the fit, scale up using proportional dividers. Pantograph tools existed in Europe by the 18th century. Maybe earlier. Maybe the Inca had equivalent technology, wooden templates, geometric scaling. Another technique, repeated fitting and grinding. Place block A. Shape block B against block A using bronze chisels and stone hammers. Place block B temporarily. Mark on high spots. Remove block B. Grind down the high spots with abrasive sand and water. Replace block B. Check fit. Repeat until the surfaces mate perfectly. Time intensive, but possible. Jean-Pierre Protzen, architectural historian who published in the Journal of the Society of Architectural Historians in 1997, studied Inca stonework. He found tool marks consistent with repeated fitting. The nubs visible on some blocks served as lifting points and fitting aids. Once the block was seated, they ground the nubs smooth. Unfinished blocks at Machu Picchu show nubs still present with smoothing partially complete. The polygonal masonry survives. Rectangular stone buildings collapse. Spanish colonial structures in Cusco fell during the 1650 earthquake. The Inca walls stood. Why? Polygonal shapes create multiple contact points. Irregular surfaces interlock. During seismic motion, the blocks move slightly but don't separate. The joints absorb energy. Computer modeling published in engineering journals in the 21st century confirms this. Irregular joints distribute stress better than flat joints. The complexity provides strength. The Inca understood this empirically. They saw what survived earthquakes. They replicated those patterns. Position on the chord represents place value. Hundreds on the top section, tens in the middle, units on the bottom. Accountants used quipu to track resources, tribute owed, stored goods, population numbers. The same base 10 logic applies to construction. Measurements in Inca architecture show modular ratios. Walls follow proportional systems. Doorways taper inward at the top. This trapezoidal shape adds stability. Wider base, narrower top. Resists toppling. The mathematics exist in the proportions even without written formulas. Less effort than lifting uphill. The site selection incorporates this. Place quarries above the building site. Use terrain to reduce work. The mathematics of force and distance apply. Moving a 1-ton block 10 meters horizontally requires the same energy as lifting it 1 meter vertically. The Inca chose locations where gravity worked for them. Each terrace level creates flat planting areas. The walls hold soil, but they also manage water. Drainage channels run beneath the surface. Gravel layers filter water. Clay layers retain moisture. This hydraulic engineering keeps the terraces from washing away during rainstorms. The slopes calculated to allow water flow without erosion. Too steep and water cuts channels. Too flat and water pools. The optimal slope depends on soil type and rainfall. The Inca adjusted based on observation. They tested. They learned. They encoded results in standard designs repeated across the empire. 3 main cables supporting the walkway. 2 side cables for handrails. Each cable is woven from smaller cords. Each smaller cord from grass fibers. Twisted tight. The cables need regular replacement. Grass deteriorates. The Inca maintained the bridges through a labor tax system. Villages near bridges had obligation to rebuild them annually. The mathematics of load distribution applied. The cables had to support the weight of travelers and cargo. The span length determined cable thickness. Longer spans needed thicker cables. Too thin and the cable snaps. The Inca understood tensile strength through experience. They built what worked. They recorded the dimensions in memory and oral tradition. No contact between these civilizations during their construction periods, yet similar mathematics appear. Pi encoded in circular structures, Pythagorean triangles in layout plans, optical corrections for human perception, material science in concrete and stone selection, load distribution in arches and domes, earthquake resistance and masonry techniques. These principles emerge independently because they're fundamental. The mathematics exists in the physics. The laws don't change with culture or time. Ancient builders discovered these laws through experimentation and observation. They encoded the knowledge in construction techniques. They passed it to the next generation through training and practice. The mathematics remained constant. Geometry doesn't care about technology. A right angle is a right angle, whether you mark it with string or laser level. A circle is a circle, whether you draw it with a rope anchored to a stake or CAD software. The ancient builders used the tools available and applied mathematical principles that remain valid today. Laser scanning reveals measurements invisible to the naked eye. Finite element analysis models stress distribution. Ground-penetrating radar maps, foundations, and hidden chambers. Chemical analysis determines material composition. All of this confirms what the structures already told us. The ancient builders knew. They knew more than we credited them with. They knew math we thought was discovered later. They knew engineering principles we formalized centuries after they built. The structures are the proof. They stand, they function, they endure. Not as accurate as modern value of 3.14159, but sufficient for construction, off by less than 1%. For a structure measured in meters, 1% error is centimeters, acceptable in practical work. The formula works. The pyramids prove it. Cut corners off. Each corner cut removes 1/9 of the square's side. This creates an octagon. The area of the octagon approximates the circle. The ratio gives pi. This method appears in Greek mathematics later. The Egyptians had it first, used it routinely. The surface area includes the curved surface plus the circular base. The scribe has it. The calculation works. This is advanced geometry, spherical surfaces, 3-dimensional shapes, 1800 BCE. The mathematics existed. Stonehenge Phase 1 begins around 3100 BCE. Ditch and bank earthwork, circular. The Aubrey holes. No stones yet, just post holes. Timber posts or markers. The circle is established. Phase 2, around 30,000 BCE. The bluestones arrive. 82 stones from Wales, arranged in a double circle. Dismantled later. Phase 3, around 2500 BCE. The sarsen stones, 30 uprights in the outer circle. 5 trilithons in the horseshoe. These are the iconic structures. The arrangement stays stable for 4,500 years until stones fall in historical times. The re-erection in the 20th century puts them back, but not exactly as found. John Wood's survey from 1740, preserved in archives, shows the arrangement before modern intervention. That survey is the most reliable record of the original layout. 4 stones marking corners of a rectangle. The rectangle's dimensions encode astronomical ratios. The long side runs parallel to the sunrise on summer solstice. The short side runs perpendicular. The diagonal of the rectangle points to the most northerly moonrise. This only works at Stonehenge's latitude. Move north or south and the geometry doesn't align with the moon. The builders chose the location to make the math work. The rectangular geometry with astronomical alignments requires knowing the azimuth angles of solar and lunar extremes. This requires years of observation, marking points on the horizon, measuring angles, recording in some form, maybe marked stones, maybe wooden posts, maybe scratches in rock, the knowledge accumulated and encoded in the monument's geometry. Outer diameter, 330 meters, 100 stones in the outer ring, 2 smaller circles inside. The geometry follows similar principles. circular banks and ditches, astronomical alignments, construction dates to 2800 BCE, the mathematics connected to Stonehenge, same culture, same knowledge base, same proportional systems. Each caryatid carved to precise proportions. Head, torso, legs all follow mathematical ratios, not golden ratio, but ratios based on human anatomy. 8 heads tall. This is the classical proportion used by Greek sculptors. The real human body averages 7.5 heads tall. 8 heads creates a slightly idealized figure, taller, more graceful. This requires measuring real bodies, establishing average proportions, then adjusting for artistic effect, all based on mathematics, all encoded in workshop practices. String stretched between them. Mark the curve with the string kept taut. This creates a perfect ellipse. The math is straightforward. The execution at this scale requires precision. The structure seats 50,000 spectators, 80 entrances, numbered arches. Spectators entered through their assigned arch and navigated to their seats via internal corridors. The circulation system requires planning, traffic flow, crowd control, exit times. This is operations research, applied mathematics. Rome had no operations research textbooks, but they understood the principles through experience managing large public events. 0.5 meter per 1,000 meters. This gradient is calculated. Too steep and water velocity erodes the channel. Too shallow and water doesn't flow. The optimal gradient depends on channel cross-section and wall roughness. The Romans tested different gradients. They learned what worked. They standardized it. The aqueducts brought water to Rome from mountains 40 kilometers away. Daily delivery, 1 million cubic meters. Enough for 1 million inhabitants. The math, 1 cubic meter per person per day. Clean water, constant supply. This requires engineering the entire system. Source, channel, settling tanks, distribution, all connected by mathematics. We write x plus x divided by 7 equals 19. Solve for x. We get x equals 16.625. The Egyptian scribe uses the method of false position. Guess x equals 7. Check, 7 plus 1 equals 8, not 19. The ratio is 19 divided by 8 equals 2.375. Multiply the guess by this ratio. 7 times 2.375 equals 16.625. Same answer. Different method. The mathematics is identical. The notation differs. This distinction matters. When we say ancient cultures lacked algebra, we mean they lacked our notation. They solved the same problems. They found the same answers. The math existed. The symbolic representation developed later. Construct a rectangle 5 units by 7 units. The area is 35. Want to find the square root of 50? Construct a square with area 50. Measure the side. That's the square root. Want to solve a quadratic equation? Construct a geometric configuration that represents the equation. The dimensions of the configuration give the solution. This works. Euclid's Elements, written 300 BCE, contains geometric solutions to equations we now write algebraically. Same mathematics, different representation. Square roots, cube roots, approximations to pi, Pythagorean triples, all dated to 2nd millennium BCE. The mathematics is sophisticated. The notation is cumbersome by modern standards, but it works. The scribes trained in mathematics spent years learning the tables and methods. They applied them to surveying land, calculating taxes, dividing inheritance, planning construction. The mathematics served practical needs. It also served curiosity. Some tablets show pure mathematical problems with no practical application. Mathematical play. Intellectual exercise. The weavers had to plan the design before starting. Count threads. Calculate color changes. Maintain symmetry. This is mathematical thinking. Applied to art. The distinction between practical math and artistic math blurs. They're the same thing. Pattern, structure, proportion. Mathematics is mathematics whether it appears in architecture or textiles or pottery decoration. Some stretch 500 meters, straight lines visible from the air. How did they create straight lines over this distance? Survey stakes and ropes. Mark a point. Walk 500 meters. Keep the rope taut. The line stays straight. For curved figures like animals and spirals, the method adapts. Multiple arcs constructed from different center points. Each arc requires a fixed point and a rotating radius. The workers had no aerial view. They worked from ground level following the geometric construction plan. This requires understanding that the local geometry creates the global shape. Each step follows from the previous step. The final result emerges from consistent application of geometric rules. The lines remain visible because the desert preserves them. Remove surface stones, expose lighter soil underneath. The contrast persists for centuries in the dry climate. The geometry persists longer. The mathematics is permanent. Commerce needs standard measures. All of this requires mathematics. The knowledge accumulates, it gets taught to the next generation, it becomes more sophisticated. Techniques improve, new problems get solved, the mathematics grows. Cultures across the world independently discover that certain ratios feel right. The golden ratio appears in Greek architecture, in Egyptian pyramids, internal chambers, and Roman building facades, not because of contact, because the human visual system responds to these proportions. Our brains evolved to recognize patterns. Certain patterns trigger positive responses. Symmetry, balance, proportion. These aren't arbitrary cultural preferences. They're biological. The mathematics aligns with neurology. Ancient builders discovered this. They didn't know why it worked. They knew it worked. They used it. The Romans built for glory and utility, but encoded mathematical principles in the structures. The Inca built to harmonize with the landscape using geometric principles that modern engineers confirm are optimal for earthquake resistance. The purposes varied. The mathematics connected them. 600 kilometers of transport. This changes our understanding of Neolithic trade networks and social organization. In 2025, analysis published in Archaeology magazine revealed sacred mathematics embedded in an ancient city's architecture in Peru. Base 10 proportional systems and plaza layouts, astronomical alignments and temple orientations, fractional measurements consistent across multiple structures. The mathematics existed at larger scales than individual buildings. Entire city plans encoded geometric principles. Other researchers debate this. They point to tool marks and experimental archaeology showing simpler methods work. The debate continues. What's certain? The precision exists, the mathematics works, the blocks fit. Whether they used sophisticated tools or simple tools applied with great skill, the result demonstrates mathematical knowledge. The angles are calculated, the surfaces conform, the geometry is exact. In November 2025, a study on Stonehenge's altar stone placement revealed fractional numerics using two interconnected measurement systems, one using the megalithic yard of 2.71875 feet, the other using imperial measures. The relationship between these systems, fractions 29 over 32 and 32 over 29. These fractions by chance or design mimic mathematical formulas related to 29 and 32 dimensions of geometry. 29-dimensional space, 32-dimensional space. This sounds absurd, but the fractions appear in the measurements. Whether the Neolithic builders understood dimensional geometry or whether the fractions emerged from practical measurement constraints, we don't know. The numbers exist in the stones. The mathematics persists. The monuments stand. The knowledge embedded in stone survives longer than any papyrus or tablet. Fire destroys libraries. Floods erase clay tablets. Conquest burns written records. Stone endures. The Parthenon stood, while Athens fell to Sparta, then Rome, then Ottomans, then independent Greece. The Pantheon survived the fall of Rome, Gothic wars, medieval flooding, Renaissance looting. Stonehenge outlasted Bronze Age culture, Iron Age Celts, Roman occupation, Saxon settlement, Norman invasion. Machu Picchu remained hidden for centuries until Hiram Bingham's expedition in 1911. The stones waited. The mathematics waited inside them. We analyze them with software simulating stress and load distribution. We confirm what the builders knew. The angles work, the proportions balance, the structures stand, the mathematics is correct. We're not discovering new mathematics. We're discovering old mathematics, ancient mathematics. Mathematics developed by civilizations we thought incapable of it. Stone Age meant technologically limited, intellectually limited. Early archaeologists attributed advanced structures to external influence, aliens, Atlantis, lost super-civilizations, anything except the actual builders. This bias is racism disguised as archaeology. The evidence contradicts it. The mathematical papyri are real. The astronomical alignments are real. The engineering techniques are documented. The tool marks are visible. The experimental archaeology works. Modern researchers using Bronze Age tools replicate ancient results. Not quickly, not easily, but successfully. The ancient builders had time, knowledge, and motivation. They succeeded. A rope, stakes, and understanding of geometry produces circles, ellipses, Pythagorean triangles. A water level and patience produces level foundations. Copper saws with abrasive sand and persistence cuts granite. Bronze chisels and repeated striking shapes blocks to exact dimensions. The tools constrain speed. They don't constrain accuracy. Ancient builders had time. Generations worked on these monuments. Knowledge passed from master to apprentice over decades. The accumulated expertise produced works we struggle to match with modern technology. Not because we lack tools, because we lack the craftsmanship, the patience, and the cultural commitment to mathematics expressed in stone. The Pantheon's dome informs concrete research. Inca stonework inspires earthquake-resistant design. Stonehenge's astronomical alignments contribute to archaeoastronomy. The pyramids remain standard references for project management and logistics at scale. The structures teach us. They've been teaching for millennia. We're finally listening. Precision-engineered hammer, stone head with drilled socket, wooden handle long deteriorated. The socket diameter, 4 centimeters, perfect circle, drilled with a hollow reed and abrasive, 9,000 years ago. This predates Egyptian dynasties by 5 millennia, predates the pyramids by 6,000 years, precision engineering in the Neolithic. The mathematics existed before we had writing to record it. The makers knew, they measured, they calculated, they manufactured to specification. The hammer proves it. The ancient builders worked with the same physics we work with. They lacked our mathematical notation, our calculation tools, our theoretical framework. They didn't lack understanding. They understood what mattered, what works. They tested, they observed, they learned, they applied, they built. The structures stand as proof. We couldn't see it because we weren't looking. We assumed ignorance when we should have assumed intelligence. Different methods, same mathematics. Different notation, same principles. Different tools, same precision. The ancient builders left us a library written in stone. Every measurement is a word. Every proportion is a sentence. Every structure is a volume. The mathematics is the language. We're learning to read it. We're learning they knew more than we credited. We're learning humility, built up in others. The foundation work required moving earth. Calculations of volume, thousands of cubic meters. Workers with antler picks and wicker baskets. Years of labor. The mathematics determined how much earth to move and where to move it. The structure required stable foundations. The builders provided them. The mathematics guided the work. The stones remain level 3,500 years later. The final lesson is this. Mathematics is universal. It transcends culture, language, time. Ancient Egyptians, Neolithic Britons, classical Greeks, Imperial Romans, Inca engineers. They all discovered the same mathematical truths, because the truths exist independent of the discoverer. A circle has the same properties in Egypt and Peru. A right angle is the same in Greece and Britain. These are not cultural constructs. They are mathematical facts. The ancient builders found these facts through observation and experimentation. They encoded them in monuments that outlast empires. The mathematics remains. The stones remain. The knowledge remains, hidden in plain sight, waiting for us to look closely enough to see it.